you would not really require to sleep. Okay, so I'll just have made some slides which I will take you through. Right. So just want to get a confirmation if you can see.
Yes.
All right, fair enough. So the difference, I think, is the following. I just want to give a perspective from the practitioner's lens. The whole idea is that machine learning today is, of course, omnipresent and present everywhere. There are challenges from the research angle, nevertheless. But what I would like to sort of highlight is what do you need to look at when you're looking at machine learning in real world scenarios. Okay. Since it's going to be a very different kind of a presentation, I just need to have this disclaimer. So whatever I speak in the next maybe 90 minutes or so are my interpretation and my views of certain things. And they don't necessarily mean that TCS agrees to what I say. So please don't mistake what I say to be that of the views of TCS. And I've used the graphics liberally. Sometimes I have quoted the source, sometimes I have not. But in case I fail to mention it, the copyright is owned by the respective owners. Okay, so this is the disclaimer I want to make. So what is it that I'm going to speak about? So I'm going to stress about the fact that there are indeed challenges when one uses machine learning, and I will be looking at it from my own experiences. So please forgive me if you see a lot of things which relate to speech, which is the current focus of my interest with my lab mates. So examples, whenever I give or cite, would come from the speech angle. Nevertheless, I'll try and see if I can give you examples outside speech area as well. The reason I chose this topic, and I think it's very important from the faculty perspective as well, is that today machine learning is almost present everywhere. Talk of anything, and the first thing that you see is we have used machine learning to do this, do that, and things like that. What is heartening is the fact that experts, and mark the word, novice experts, everybody seem to be using. So machine learning outputs have given, in some sense, some kind of a tool which makes even the novice feel that they are experts, which is good. However, there are certain pitfalls and challenges that one needs to be aware, and I will try and point out a few of them as a practitioner of machine learning. Now, before I jump actually into machine learning, I would like us to look at what is it that forces us to look at machine learning. Look at all the words or all the sentences that I have here. You may say, what is he going to speak in this lecture today? So those of you who own a Google Home might say, hey, Google, and ask a question. Or those of you who have an Alexa would say, when is the best time to visit Mumbai? Or if you're doing a search on a DuckDuckGo on the web, you may ask, how do I cook a healthy snack? Especially because you're at home and your kids may need a snack which is healthy. Or you may ask your own mother, where was I born? So there are lots of things that you have queries about. So if you look at the common thing in all these things is the what, when, how, where, who, why. So these are the common things which make us, what I would say, hungry for information. So this picture, of course, is not mine. It is picked up from the web. So the whole idea is we are very, very curious about lots of information. And this information curiousness is not very new. If you look at even the 1902 novel or a storybook by Kipling, where he says that he has 6 honest serving men. Okay, men today may not be correct. So I've just changed it to people. They taught me all that they knew, and their names are what, why, when, how, where, and who. So if you look at information, the importance of information, from the journalism perspective, if you look at it, this is a single short formula to get a complete story about a subject. So if you were to look at any story that is being served in a newspaper, you need to ask the 5W1H questions to make sure that the story is complete. So for information gathering, you need to be able to ask these questions and get that information. So these are, I would say, the basic ingredients to solve a problem. So gathering information to solve, so basically what we are saying is, to solve a problem, we need to gather information from data. So let's go on to the next slide and say, if you want to gather information from the data, what is it that you need to do? So the middle block, as you see, you have to ask the right questions. So you have lots of data that's lying around. Unless you ask the right question, you'll not get the desired information that you're looking for. So for those of you who want to know what this data means, probably it is signal, or in the terms which are more popular these days, it could be the image data, speech, it could be text, it could be anything coming out of sensor. And asking the right question could invariably be tuned as the analysis of that data. And information is something that has to be useful. So the important question is, how do you learn to ask the right question? That is, given the data and you know what is the information that you're looking for, how do I ask the right questions to get the information that I want from the data that I have? So if you look at it a little more carefully, if you want to learn something, you need to learn from somebody. In this thing, it could be a teacher, it could be the world knowledge. You have some information about the world, and hence you are able to learn from, so that you learn to ask the right questions. And what you really need is, you need to know some knowledge about the data. And also important is, what is the information that you are looking for? Okay, sorry about that. So if you ask a machine to do this analysis, or ask the machine to sort of learn to ask the right question, you would in some sense say it is a machine learning kind of a process. So in a very crude definition, machine learning can be looked upon as a process which enables us to teach a machine to learn to derive the desired useful information from the data. So it is very simply said, if you're able to teach a machine to derive the information that you're looking for from the data, more or less you could turn it into a machine, call it as machine learning. But since I'm speaking to the faculty and they would insist on being formal, so the best way to look at a formal definition is, machine learning is the study of computer algorithms that improve automatically through experience. So that is from the wiki, it's not my definition. Or machine learning algorithms build a mathematical model based on sample data in order to make predictions or decisions without being explicitly programmed to do so. So probably this is the kind of definition that you would tell your class students. But for the sake of simplicity, I will stick to the fact that any process which will allow you to teach a machine to learn so that it derives the information that you're looking for from the data, loosely we can term it as machine learning. Now let us look at what are the challenges that come because of that. Now the thing that could be happening is, the same data, you could be looking at different information. Let us look at this example. As I promised, I stick to speech. Sumit, my son, who probably came in the morning and said good morning to me. So let us look at that signal. Namita, my wife, she also came and said good morning to me. Let's mark it as signal. If I were to sort of try and assess what is it that they said, then both the signals that's spoken by my son and by my wife, I should be able to comprehend the words, the linguistic content, good morning. But if I were to sort of try and understand who spoke, then I should be able to relate the same signal S1 to the name Sumit and S2 to the name Namita. If I wanted to go deeper and say, what is it, how did the say it, then probably I could have felt that Sumit was much happier and Namita was neutral when she said the good morning. The other kind of information that I can derive, even if I didn't know them a priori, is probably I would be able to guess that Sumit is a boy and Namita is a female, and probably age to some extent. So the crux of it is the same signal, S1T spoken by one person, S2T spoken by another person, but there are so many different things that you can look at it. So the challenge in machine learning, so to say, is how do we make sure that the machine is learning what you want it to learn? So you have the same input signal S1, S2, but in one instance you have to be able to say good morning. Other instance you have to be able to say it is Sumit. The third instance you will have to be able to say that it's happy or the age of the boy, etc., etc. So let us look at what is it that you can do. So actually, if you look from the speech perspective, I know some of you are experts in the speech signal processing area. So if you look deeply into it, before the deep learning era, people had two different types of features that they used. One was from the listener's perspective. One school of thought is eventually the speech is going to land up in somebody's ear, so we should be able to model how the ear functions, and there is one set of features called the MFCC, Mel frequency capsular coefficient, which they say is what we should model the speech as. Okay. The other perspective is, irrespective of who listens, it's the speaker who delivers the speech, and hence we should be able to model the speech in terms of whatever is required to model, in this case, the LPC. Now, this debate has been on for a long time, and the people have derived and said that, okay, this kind of features work well for speaker biometric, this kind of things work well for speech recognition, for emotion, some other set of features work. But because of the machine learning popularity, or the deep learning in speech popularity, because of the abundance of data that you have, and also the availability of faster machines that can process data so that you can do lots of experiments quickly and then turn around, people started saying that let us keep the feature debate away. Let's start using the raw data. So one good thing that has come out of deep learning or machine learning in speech is that now you don't need to choose any features. You just give the raw data. However, once you do this, while it is good for you, you cannot be sure what the machine learning algorithm or machine learning box is learning. So this challenge is always going to remain. So to just extend, what is the varied kind of information that exists in speech data? Let me try and see if I can play this.
Truth persists. In the midst of darkness, light persists.
So this is a spoken speech. Were you able to hear that?
Not really.
Okay.
It was very noisy.
Okay. Yeah, my apologies, but it is a utterance by a male in some form. Okay, maybe it's not very important. Let's go ahead and see. So if you just believe that that was an utterance by a person, so there are different kinds of things that you could use. You could sort of gauge the gender of the person, the emotional state, the speaker name. In some sense, the person who spoke it. The other thing you could say is in what language did they speak, and what is the textual content of what they spoke. And the third thing probably you would say is how well it was spoken, the quality, manner, etc. So while you could not hear what I played, but you will have to believe that it was by mail, and it was a utterance, or it was a sentence picked up from Mahatma Gandhi's speech. Okay, so I thought this is the best way to put, especially considering the fact that yesterday was October 2nd. So the language spoken was English, and what he spoke in that sentence is, truth persists in midst of darkness, light persists. So if you look at what is the importance of what I wanted to share is that the same data, you have lots of different varied information that you could derive. So what I have captured in this diagram is if you have one spoken speech, you could say the what, the who, the how, and then you could say the gender, etc., etc. So there is just one thing, but you have several things that you can actually derive. To the left is what I would call as data, and to the right is what I would call as information. So to derive the information from the same set of data, you need to be able to learn. Okay, so from the machine learned perspective, any aspect which allows you to automatically extract the information that what you see onto the right from the speech signal which is onto the left could be turned as some kind of a learning. So you could say what is this? It could be speech recognition, it could be speaker, it could be accent, it could be emotion, etc. Now, those of you who have been carefully looking at the 5W1H kind of a thing would generally try to tend ask, what about the where, when, and why? So there are these aspects which are not readily derivable from what was heard, the utterance. So for this, you need to have some world knowledge. You need to have some metadata associated with the audio to be able to derive the thing. But nevertheless, the majority of the information seeking attributes can be addressed by just looking at the speech signal. One thing you would have immediately realized is the fact that given a spoken sentence, let's say the one that I just mentioned, good morning by Sumit, as a human, you can do this all simultaneously. I should be able to say what he spoke, who was the person who spoke, what is the category of the boy, which language, etc., without having to sort of have to focus on anything. I know everything in one go. So the challenge number two that you would see in machine learning is, what do you want to do? Do you want to learn each task individually? That is, you want to recognize who spoke as one machine learning model, what they spoke as another machine learning model, or do you want to learn all the tasks simultaneously? Especially this becomes important considering the fact that the input data is the same. So those of you who have done courses in machine learning would have come across what is called multitask learning, which is getting very, very popular these days. Let us look at the machine learning challenges from an aspect of the fact that machine learning is everywhere. Now, the current scenario seems to be that there are, of course, machine learning conferences, but every other conference, be it the signal processing, be it material science, aerospace, pick up any conference, it has a large section of papers in machine learning. So you would have a dedicated section on machine learning. And it's not very difficult to guess why. Why is it that machine learning sections are there in almost all the conferences? The reason is very simple. There is a lot of data explosion and the availability of GPU, that means faster computing. And data explosion is actually activated by the fact that sensors are getting cheaper. So if you look at the combination of all this, data explosion because of cheap sensors and faster computing, human analysis or humans' ability to do anything about that particular volume of data, the velocity of data makes them incapacitated. And the fact that data crunching comes from faster computing allows you to identify patterns. It doesn't need to really know how the patterns are identified, but it's a black box learn. So the fact that you could use machine learning algorithms to crunch data to identify patterns without knowing exactly how it is working is another reason why machine learning is everywhere. And the third thing that catches one's eye is the fact that these have always invariably resulted in impressive results, be it the video, be it speech processing, autonomous vehicles, whatever you say. You have everywhere machine learning. So all these three combination is what I believe makes even a novice feel that they are experts. Now the challenge three is when do you use machine learning and when not to use machine learning? The reason I put this as a challenge is I've had occasions where I've seen people use machine learning because that's something that is easy to use because the tools are available without really questioning when should I use and when I should not use. So just to give a glimpse of a feel for when machine learning to use and when it's not to be used, from the industry for perspective, technology for first aspect is something that becomes very important. So the question to ask is, what are machines good at?
Excuse me, somebody, please put your mic. Please mute your mic.
Yeah. So if you look at what are machines good at, probably the first few things that comes to our mind is that they are able to crunch numbers faster. They are consistent, and they don't have biases like we as humans have. And of course, there is no fatigue. And if you ask a reverse question, what are most people not good at? Probably these are the same things that we are not good at, whatever the machines are good at. And what are people good at? Probably they're good at reasoning, they're good at logic, social skills, comprehension of language, etc. So if you look at it, we people are good at certain things only when the data is limited. If you throw a large amount of data, a large amount of world knowledge, probably you will not be able to assimilate it. So the answer to challenge number 3 is you need to have a mix of both. You need to have machines, use the ability of machines to number crunch, its consistency, human bias, etc. Also, you will have to have some places where you need to get your people sense into you need to exploit the complementary aspect. So we saw that data explosion, cheaper sensors makes machines in an advantageous position. But what is it that makes a machine in a disadvantageous position? So that raises to what I would call as challenge number 4, the machine's inability, the machine learning's inability or the lack of ability to explain. So what we saw, and I've been mentioning, is the fact that deriving information, which what is the information that you want, let's say, from the data, is in some sense a magic box or a black box learn. You don't really know what it is. So you cannot explain how the information was derived, except that it seems to be doing what is expected. Let us look at 2 examples. This is an example that I quote often because this has stayed stuck in my mind, because when my son was maybe in the 3rd or 4th standard, his maths teacher gave him a question which asked, find the odd number out of 11, 21, 31, 41. And to my surprise and to the teacher's surprise as well, my son wrote 11. And of course, he got marks knocked off. So when he returned home, I asked him do you think this answer is right? And he said, yes, it is definitely right. It did puzzle me, but being a little patient parent, I asked him, how can you explain this answer? Because I think 21 is the right answer because the rest of them are prime. He said, look, if I were to reverse the digits, 21 would become 12, 31 would become 13, 41 would become 14, but 11 would remain 11. He again said, look at it, you put a mirror below this, 11 will remain 11, 21 will not remain 21, etc., etc. So from his perspective, his ability to explain, 11 is right. Okay, it may not fetch him marks, but if I were to not understand why 11 was an answer for this particular question, I would always think that the learning mechanism of my son was not right. But after listening to him and keeping maths a little aside, it does show that explanation always helps. So it may be doing certain thing, the machine learning algorithm, but if you are not able to understand what it is doing, you would not be able to interpret whether it was right or wrong. Let us look at the importance of explainability from the medical surgery recommender perspective. Suppose you have you have a disease which needs an operation, and there is an explainable system which says there is a 50% chance that you have to go through an operation, versus a black box which says that 99% I'm sure that you have to go through an operation. So if this was a question that was posed to one of us, it would take a lot of effort for us to sort of choose the black box one, because even 1%, even if it was not trained, but if it was not explainable, I wouldn't be too eager to go undergo an operation. So the explainability is a very, very important thing. So when you do machine learning, you will have to sort of bring in the explainability aspect. Otherwise, it is not going to be accepted in the real world scenario, especially in the medical. This challenge number 5 is you need to be aware. The machine learning is not aware whether the data is comprehensive and complete. It doesn't have any sense of the, it just has a data sense, but it doesn't have the world knowledge. For example, those of you who are doing natural language processing would sort of look at words and then look at what are called the embeddings, the word embeddings, the BERT embeddings, or the glove embeddings, and things like that. But from the machine learning perspective, it doesn't make sense for it. Sunil is same as Kumar is same as any other word, human, for example. It doesn't really understand. So it is not the machine learning's ability to understand whether the data is complete. So this is a very popular example that I often cite, and it's not my own, that during the World War II, there were a lot of fighter planes that returned back having been shot by the enemy guns. So the question that the Air Force officers wanted to sort of ask themselves is, where should I put the most important protective gear shield on the plane so that the planes would not get shot? But what was missing is the fact that there were a lot of planes that never returned. So those planes had data which they didn't have access to look at. So if you were to do machine learning on all the planes that returned, you would not be able to assess or analyze planes that never returned because they fell down because they were shot at strategic position. So it's very important from the practitioner perspective to be conscious of the fact that there might be some information which is not part of your data set, which is something that you still need to learn. So this is a challenge for machine learning. There's no way of knowing it. You need to be able to put that into focus. Challenge number 6, the machines only work on what they have seen. So if they have not seen something during the training, it would be something that they would not be able to do anything about. So they don't have any world knowledge. So the importance is, what do you do in case of data that is not been seen? The classical example is there are this loan giving applications, machine learning algorithms which will determine whether you are eligible for a loan or if you're not eligible for a loan based on lots of parameters, which of course the banks never tell you what is the parameters they use. But immediately all these machine learning aspects fall into pit when there is a new customer. You have a customer about whom you have absolutely no information. How do we go about sort of determining whether he is eligible for a loan or not? So there is this drawback from the machine learning perspective. So machine learning definitely has limitations. It has a lot of challenges. Of course, we have to not forget the fact that there's nothing like logic, social skills that the machines are aware of. So let us look at machine learning a little more closer. So like I mentioned earlier, speech signal is something I cannot leave off my slides. But for the sake of this particular presentation, let's look at it as data. So you need data, you need to do some learning out of it to derive information. Let us look at the details of machine learning. So I'm sure that this is something that has been covered, but what I would like to sort of briefly put together is for training purposes, training a machine, you need to be able to have access to the labeled data. What is labeled data? The training data and the information associated with that. So if you have both the training data and the information, the label associated with that. The second part that usually people do is to extract some kind of features from that and use that features and use some kind of a machine learning method to model the features. And when you want to test these machine learning algorithms, what you do is you follow the same two process where you extract the you extract the features from the data using the feature extraction that you use for the training purposes, and then you pass these features through the model which has already been learned in the training phase to determine the label. Fantastic. So what are the challenges that you would come across? Now, the challenge, one of the challenges that you would come is, what are the features that I need to extract from the signal or from the data? So like I was talking about NLP, if it is a text, so what kind of an embedding should I use? Should I use the BERT embedding? Should I use a GLOVE embedding? Should I use something else? From the speech angle, it could be, should I use MFCC? Should I use LPC? From the image processing perspective, probably it would be, should I use edges? Should I use corner points? Should I use the intensity? What should I be using? So these are something that you need to be able to determine to get your machine learning up to date. And since you must have come across a lot of machine learning methods and techniques, algorithms, you will have to determine what is the machine learning method that I should use. So often I've found people just throw in one machine learning algorithm after another and then say that, okay, the SVM works best or the AN works best. But if you had some more knowledge about the data, probably you would be able to determine even before you started your experiments as to what is it that I should be using. Well, these are well known. The challenge number 8 becomes a very crucial thing. From the academic perspective, we always have access to data. When I was doing my PhD, I never questioned the images that I got. I just used them, did my algorithms on that, and got the information, and then compared the SNR or whatever, and was quite happy. But once I finished my PhD, I realized that you need to ask a lot of questions about the image itself. How was the image captured? What was the lens that was used? Did the lens have some kind of a distortion? Are the intrinsic parameters of the lens known? And what? These are the kind of information I never questioned in my PhD, because to me, image was the thing. But you need to be able to understand the context in which the data was collected to be able to sort of be able to determine what exactly you need to be doing. The challenge number 8 is the actual availability of training data. In real world problems, getting this kind of information is very, very hard. I'll be telling you in a couple of slides from now why it's very hard. And the challenge number 9 is the fact that we have the data set given to us, and then we use the training algorithms, and then we use the test and then report an accuracy of, let's say, 90%, 98% using this particular technique is valid only when the train and the test data belong to the same distribution. They have been captured at the same time or under similar circumstances. But in real world problem, it is never ever the case. The test data is going to come from scenarios which are not necessarily what your model has been trained for. So this is a challenge that you need to keep in mind. Let us look at one example from, as I promised, this is going to be from the speech thing. So in the training phase, let's say you have labeled audio annotations. Maybe you have annotation which says that this is angry speech, this is, let us say, neutral speech, etc. So what you really do in the training phase is segment the audio into smaller parts. Because of the non-stationarity property of them, you try and make it into smaller parts so that they become stationary. And then you'd say that let me extract some features from that audio, some appropriate features. Important thing to note here is appropriate. We don't know what they are, but you need to have some knowledge about what is the information that you're looking for, so that you can think of what is that appropriate thing. Then you select some kind of a classifier. You need to select that. And in the test, you use the same classifier and get it there. So like we saw in the earlier slide, the choice of speech features is important. The choice of classifier is important. The availability of training data is also something of a challenge. But the major challenge comes when you get into the real world condition is the accuracy of annotated data. So you have data which has been annotated. By annotation, I mean from the speech angle, you would say that, okay, this is the speech and I think the emotion is neutral. But you are not very sure what is the accuracy of the annotation, what is the degree of noise. Another challenge that comes is, do you have sufficient data for all the classes? So what happens very often is you have a large amount of data for one class, and you have very small amount of data for another class. In that kind of a scenario, it becomes a different kind of a machine learning. You cannot do the standard machine learning. So let us look at, from the practitioner's perspective, what one would say is, I've seen many people say that, okay, today the level of performance of the machine learning algorithm is, let us say, X%. If I want to make it X plus percent, give me more data, more data, more data. So if you look at this from the data angle, what's it that one is talking about? Of course, machine learning has not been new. There have been machine learning aspects even before it became very, very popular, and it has been being used in all over the places. When the machine, the amount of data was small, rules and explainable heuristics is what we all used. I'm not too sure about the people who are listening to me, but people who are in my age group, probably we have all used this. Now, if the data becomes large, if the velocity with which the data is coming is dynamic and huge, you have no option but to look at machine learning aspect. You cannot build rules with this kind of data. So from the machine learning perspective, data is good. Okay, lots of data, not a problem. As we saw earlier, cheap sensors, continuous data streams, and all of us are giving out data whenever we use any application on our mobile phone. So there is an abundance of data, no problem at all. But the challenge is the annotation of data. Be it supervised, semi-supervised, or unsupervised learning, you need annotated data. Let me take you through one example as to what I mean by a challenge in annotation of the data. As promised, again, I stick to the speech as an example. Let us look at this particular picture, and the context that we want to do is to learn emotion recognition. Okay, so we need to build a machine learning algorithm or a machine learning instance which can sort of look at the audio file and say what is the emotion recorded in the audio file. The interesting point here is you have two references or frames of reference. One is a speaker, the other is the person who is listening to the speech, and speech is in between. From the speaker's perspective, you could say that if he or she were to label the data, it would be what I would call as the encoded data. So encoded emotion is the exact emotion felt by the speaker. So when I'm speaking and I say that I feel happy when I speak to all of you, so the delivery, the audio that one might be recording should be labeled as happy. But the downside of that is that you have a label coming from a single person. How do I believe that I was really happy when I said that I was happy? There's no way of distinguishing. The second way of encoding or sort of labeling the emotion that we heard in the sentence is by the listener. So this is the perceived emotion. So the person doesn't have any clue what the speaker felt when he delivered that particular utterance, but he would perceive the emotion of the speaker by listening to what it has to say. Now, the advantage of having a decoded emotion, that is a person who is listening, is you could have many people listen to the same conversation and then ask them to sort of label the data, annotate the data. Now, the question to ask is twofold. One is, what is the true emotion? Is it the one that is expressed by the speaker, or is it the average of the emotion as perceived by the people who are listening? So there's no way of saying which one is true and which one is not true, but there is this challenge of this perceived thing. The importance of this particular emotion labeling is important, because I've found lots of people use the annotation from the encoder perspective to model something, to test it on the decoded emotion. It's never ever going to work. But if you don't realize that these are two different things and start using the same machine learning kind of a process, you are going to run into it. So you have to be conscious of the fact that you have to know how the annotation has been done. The other thing from my own experience is the consistency of the decoded emotion upon the different raters is very, very poor. So those of you are aware of the kappa score would find that it is something of the order of 0.21. So annotation becomes a very important aspect in the machine learning perspective. Then the second, the other challenge is I've run out of numbers, so I've not put the numbers. Okay. So the availability of clean data. So when you want to a machine to learn, you always insist on the clean data, but it is never ever the case when you look at real world problems. There are noises. When you listen to me, probably the fan that is sort of rotating on top of my head is also passing out some information. But noise in today's world is not really a noise, but it is also data. So you'll have to sort of deal with that. So when you're doing machine learning, you have to be conscious of the fact that you will never ever get clean data. The third challenge that I have put here is the balance of data. So let's look at some of the examples about what I mean by data imbalance issues. So most of us today would call up call centers to have some problem with our mobile phones or something that has not been delivered, especially since these days everything is being delivered home. You would have a lot of complaints. But people who call the call centers are most often angry and less happy. So if you were to sort of try and say that, let me try to machine learn the audio emotion from a call center perspective, you would land up with lots of data, audio data corresponding to the angry customers and very, very less corresponding to the happy customers. So you have this data imbalance. So when you want to do machine learning on such data, if you start using machine learning algorithms that one looks at from the theory perspective, you would run into deep problems. And the second example is a credit card fraud data set. Those of you who have played with this kind of a data set on Kaggle would see that the number of fraudulent transactions is way smaller than the normal transaction. If I'm not mistaken, I think the percentage of fraudulent transactions is about 2% compared to 98% of normal transactions that are going to happen. So you have one class, which is the fraudulent class, which is just 2% of your data. And you have normal transactions, which are about 98% of the data. So how do you learn from such imbalanced kind of a scenario? And with how can we forget COVID? With keeping COVID in mind, even if you were to look at the lung X-ray images, and if somebody wanted to machine learn, given an X-ray image, whether it is a COVID positive or a COVID negative, you would run into the same kind of a thing. You would have lots of data which correspond to healthy people and not very few. And this is true for most of the medical kind of a scenario, the MRI to detect tumors, etc. The important thing to look for, this is something that I've come across when people using these kind of data sets publish their results, they would invariably talk about an accuracy. So just to give you an example of why this kind of data would result in not the correct interpretation of your machine learning. Suppose you have positive samples, which are the healthy samples, let's say 19, negative samples 10. So there is an imbalance ratio of 9:1. Let us say the true positives out of 90, you got 85 right, but the true negatives, you got only 1 right. So you would report an accuracy of 86%. But the true fact is the fact that the negative samples are the most important thing, because from the credit card fraud detection, you should be able to detect the frauds which occur very less number of times more often. But in this case, the negative sample, you have only detected 1 out of 10, which means you are detecting all the things that you really don't want to, but wherever you had to, you are missing out. But if you use an accuracy as a score, you would land up with a number which seems to indicate that the machine learning algorithm has done a good job, while in reality, it is not doing what it is required to do. So this is not any new thing, but the caution to use is probably you need to be able to look at from the sensitivity and the specificity aspect. So instead of reporting accuracy, you need to be able to report the sensitivity and specificity, especially when there is an imbalance in data. Completeness of data is something that we have discussed earlier as well, when I talked about how do you make sure that the data that you have is complete and comprehensive. Classical example would be, let us say you have built a language processing or the natural language processing system which has some kind of an vocabulary. A new word turns in. What do you do with the new word? So you can never guarantee what will happen with the new word that has come in. So there are lots of these completeness of the data in from the perspective of what do you do when the train, the test data are different. These challenges are something that you would not come across when you're using data sets provided by entities or which are already there in Kaggle or on the go.in website where lots of such data is available. But once you come to the real problems, all this become a reality. You don't have any of these things in terms of you cannot be sure that the data is complete, etc. So it is not just the quantity of the data, but you are looking at the quality of data. So the quality of data is something that you should be able to gauge before you can actually start machine learning. So this is more tongue-in-cheek, the practical machine learning, if you were to sort of look at from the expectation reality perspective. So most of us, when we have good data set, would plan something like you see in the top figure where you have a smooth path. But in reality, it is not as smooth. Right? There are lots of pitfalls, lots of things that you need to conquer, and these become interesting, and that's why you need to be aware of the challenges that we have. So another way of looking at it is data at the tip of the arrow and information at the thing. So the expectation is, given the data, you would get the information, but in reality, what you really have to do is it's quite convoluted. Okay. Now, I think when I was looking at my slides the other day, I felt that the first question that you may ask is, okay, you seem to be saying so many things, but why should I listen to you? So let me take you through a couple of things that probably might give you an impression that it is worth your time to listen to me. So these are some of the things that we are building as a team in our lab. As Professor Patnaik mentioned, I work for Tata Consultancy Services, and we have what is called TCS Research and Innovation Labs. And the things that we are looking at is, in some sense, build intellectual property by doing some kind of exploration. So the idea is to build intellectual property which can actually solve some real world problem. Some of the things that we are looking at are listed here. We look at speaker and speech recognition. We have been looking at distant microphone speech recognition. We have also been looking at pathological speech. So this is something that probably I will cover in subject to the availability of time, things like that. One important thing that we are looking at is how do we bring in empathy to conversational interfaces. So those of you who have used Alexa and Google Home in your offices or at home would realize that these conversational interfaces are not very empathetic. Irrespective of your mood, they would sound always the same. So which is not always a good thing. This is to give you a glimpse of the patents that we as a lab have built, which in some sense are things that we would like to turn into solutions. So this is a list of patents that not all of them are old, but maybe some of the newer ones are something that I have not yet put here. But the whole idea is to build solutions from exploration. So we have, as I speak, what is called the goodness of pronunciation, the ability to sort of gauge what is the kind of pronunciation that a person is doing. This becomes important, especially when you want, let's say, a Japanese kindergarten student who wants to be able to speak English as well as they speak in the United States. Then we have what is called an agent assist, which is able to tell what is the speaking rate of the person who is speaking to a customer. While this may sound not very interesting, but if I give you a perspective, you would see the usability of an agent assist. Most often, when we are from India, we tend to speak English very, very fast. Like you would have observed that my speaking rate is pretty fast. This is something that comes very natural to us. for some reason, and this is something that we cannot have a in some sense we are unable to control it unless we are told. So this agent assist is a small device which allows you to track your speaking rate in real time. So look at a conversation between an agent and a customer who is not from India. So if the agent were to speak very, very fast, the customer wouldn't be able to comprehend what he's doing, and the call conversation would end up being what I would say the customer being dissatisfied. So this small device that we built, it's a software assistant which would prompt every 1 second what is the speaking rate of the agent, giving him or her the ability to control the speaking rate so that within the call they can actually manage to retain the customer satisfaction. So these are the solutions that come out by understanding what is it that you need to derive from the speech data. So we have several other things that I have listed here. Some of the other things that come out of the work that we do are books, which Professor Patnaik mentioned. These are two of the books that I have put here. And also some of the applications that we build and sort of sample out. Those of you are interested might want to look at audio emotion, which is an application which can gauge the emotion of the speaker in almost real time. We are also building what is called ASR on the edge using deep speech. The whole idea why I wanted to bring in this perspective is that to build realistic applications for the real world condition, you need to be aware of the kind of data that you're looking at, the kind of information that you want to derive from, to be able to gauge what is the kind of mechanism that you would want to use. So you can no longer look at a black box learning. You need to be able to have a mechanism which will explain exactly why it's doing what it's doing. Now, these, when you look at most of the challenges that I have said, which are very many, these are very specific and very generic in nature. But there are lots of application-specific challenges that I would like to highlight. Let us look at one particular scenario where you have a to reuse a general purpose automatic speech recognition engine. So just to give you a glimpse of what this speech recognition engine is, what you see at the middle is the speech recognition engine. To those of you who have not worked in speech, it is a simple speech input and the linguistic content that was present in the speech coming out of text. For example, if I spoke good morning, the text would be GOOD space MORNING morning. But what is actually sitting behind this is a lot of machine learning aspects. So there is this acoustic model which sorts of takes the phones or sounds and makes them into words. And these require a lot of training. You need large amount of speech data, which you need to train using a different kind of, you need to be able to machine learn that so that next time audio comes, you should be able to convert that into words. Then there is a second learning module, which is the statistical language module. In this, I put it for short as language module. And this is also a learning mechanism. The whole idea of bringing in this into the focus is to say that there is a lot of machine learning aspects in a simple thing called general purpose ASR. So if I were to look at a general purpose ASR, which is often built for people with normal speech, if you were to give this general purpose ASR pathological speech, by pathological, I mean people who may have, let us say, difficulty in speaking. Let's say, look at the elderly who may have not so much control over their articulators, and hence they may not be able to produce the same thing. So in this case, what happens is you get misrecognized text. The reason you get misrecognized text is because the learned system, the general purpose ASR, automatic speech recognition engine, is not been trained for the kind of data that you would use. So this is to be expected because the machine learning has not, you're looking at unseen data in some sense. So the goal of an inclusive automatic speech recognition would be that any speech, it is pathological or normal speech, you have some kind of a machine learning algorithm which would enable you to use the general purpose ASR, so that even if it is a pathological speech, the machine learning process would convert it into a form which would enable a general purpose ASR to recognize the text as it would do for normal speech. So what are the challenges in this kind of a scenario? Suppose you want to build a machine learning system for any speech, including pathological speech. So the data collection becomes a huge challenge. So why is it a huge challenge? You're looking at people who have difficulty in speaking. If you're looking at people who have difficulty in speaking, getting data from them is quite, I would say, inhuman. So somebody who has difficulty in delivering speech, and you go and asking them to say that, please say these words so that I can build a system for you, seems to be a little inhuman to do. And of course, there is speaker fatigue. The other aspect is, of course, the annotation aspect. So normal speech, most of us would be able to annotate very quickly and correctly. But when it comes to pathological speech, it's not very easy to even annotate. So there is difficulty in annotation. So from the specific application perspective, these are some of the challenges that you would come. The other challenge would be that while you can collect normal data from any environment, collecting data from pathologically induced speech would be that you would have to go to the clinical settings for the audio data collection. But when you want to use it in real environment, you don't have the data. Recall that I mentioned that the data that you test for should be the data that you learn from. So it becomes a data differences in data in terms of what is used for training and what is used for in the real environment. Data skewness, of course, is a challenge in this case. How much data can you get from people who have pathological condition? And more interestingly, like many other applications, is that while there is some kind of a consistency in normal spoken speech, there is no such consistency in pathological speech. So the range of speech that could be categorized as pathological speech is very, very wide, which means if you would not be able to find a cluster which can put all the pathological speech in one place. So these are some of the challenges that come into play. So I know I have not kept count because it kept going ahead in terms of the challenges. But in a slide, if I were to capture, there are some high-level challenges, there are data-related challenges, and there are very, very specific challenges. So we have covered this in the previous slides. There may be a few challenges that I might not have covered, but more or less, this is the kind of challenges that we have. So let us try to see how does one really overcome these kind of challenges from the perspective of realistic condition. So I would like to sort of take you through maybe one or two examples and say understanding the data probably poses a much better way of overcoming these challenges than trying to build machine learning system without actually knowing anything about the data. So I will take you through what is called a data challenge that TCS participated a couple of years ago. So this is basically a small data set from the Far Eastern Memorial Hospital, and this was part of a data challenge, part of the Big Data 2018 conference. So there were two tracks. One was to detect pathological speech from normal speech. And then there was a second task which was required the pathological speech to be able to be classified into one of the four things: neoplasm, vocal plasa, palsy, phonotrauma, or not four, three classes. So the data that was given was normal in the form of 50 samples or 50 people, of which 20 were male and 30 were female, and pathological samples were about 150, 78, and 72 as the distribution. And the rest of it I've just put down to give you a class. This is a classical case where you have more number of pathological samples than the normal samples. The reason for this is because this is a curated data set which has been sort of curated by a set of people and made available for use. But in normal circumstances, you would have lots of normal speech and far too less pathological speech. And the most of this data was about 3 seconds long, and these were just oval sound which was recorded at a certain frequency. Now the point is this a easy problem to solve? If you look at task 1, you just need to be able to say whether the given speech sample is pathological speech or a normal speech. It's a simple binary classification. In the second task, you just need to be able to say it's a 3-class problem: neoplasm, vocal palsy, or phonotone. Since we were not able to listen to my previous audio, I will not be playing any of these samples, but rest assured that there are these audio samples which are part of this challenge. So in some sense, if you look at the whole data, it was just 37 minutes of the training data. So it is not that you could do any deep or machine learning, though it was part of a IEEE big data challenge. The importance of data visualization or understanding data is what I want to stress. Is the problem easy? If you look at if you were to extract some features from the pathological data, that is PT, NP, and VP, and if you were to look at the top 2 features plotted on the X and Y axis, you would see that they are sort of you are not able to cluster the data into 3 good segments, while there is a lot of intermix. So the thing that we went through and which I'm emphasizing here is to sort of say that let us look at the data and see if there are any properties that you can exploit. And this is something that we figured out by looking at by analyzing the data. If you looked at all the 3 pathological speech together in some feature space, you would find that they're all not something that you cannot be able to cluster. But if you took 2 at a time, as you would see on the top right and the bottom 2 graphs, they are fairly separable. So this is the understanding about the data that led us to propose a system which was able to sort of knock the first position. So the idea is very simple. Instead of looking at a 3-class problem, why not look at this as a 3 2-class problems? So you have classifier C1, C2, and C3, where you do the training with healthy and neoplasm, healthy and vocal palsy, and healthy and neoplasm and vocal palsy. So each of the classifier performance was optimized using a feature selection process, giving 3 different features. So classifier C1 had a different feature set, classifier C2 had a different feature set, and classifier 3 had a different feature set. So this is the kind of information that we derived by trying to understand the data. So when we came to the testing, what we would do is you would pass the test utterance through all the 3 classifiers. Note that for C1, you would have to extract different features, C2 different features, and C3 different features. And if you have put them all together, you would come up with an overall system like this. So just bear with me for this huge figure. But what you see to the left is the test utterance. We use the MO large feature extraction, large number of features. So the F1, F2, and F3 would allow you to choose feature selection. So F1 would choose features which are good for healthy and neoplasm. F2 would choose another set of features which are good for healthy and vocal palsy. And F3 would allow you to do that. So the output of each of this are nothing but the log probability scores, which you would sort of AND them and figure out whether it's a healthy speech or a dysarthric speech, pathologically affected speech. So the top box would return whether it is healthy or no. Healthy if all the 3 classifiers say healthy. If at least one of the classifiers, F1, F2, C1, C2, C3 says it is not healthy, it would go into the second block, the classification block. So here again, you have a different set of features, and the output class, so the C4, C5, and C6 are again different classifiers, which again do only 2 classes at a time. So the whole idea is that the observation that this class observation about the data enabled us to build this overall system. So while this may seem like boasting, the thing that I would like to point out is the fact that the first and the second rank, there was a difference of about 1.5% on a score, is something that shows the fact that you need to be able to sort of look into the data to be able to identify what is the right kind of processing that you should do. So luckily for us, we were able to visualize the data, or we took the effort to look at the data. So that is something that we again applied to Alzheimer's diseases. There were 3 classes: healthy, controlled, mild cognitive impairment, and Alzheimer's disease. The fact that using a 3-class classifier is not a good idea can be immediately sensed, because the mild cognitive impairment is neither healthy control nor Alzheimer's. So it stays in between, and it's very, very difficult to classify that. So in this case also, while we looked at the data and we had the results from the FEMH data challenge, winning that, that we came out with a similar model which would able to look at 3 2-class data. The second thing that I would like to emphasize is the importance of looking at imbalances, or looking at data which is not sufficient. So this is based on some of the work that we did earlier, which has appeared in Sadhana. Those of you who are interested to take a look at this particular paper in Sadhana. So the motivation for this simultaneous 2-class learning. So what is the thing? The observation is that very often in real conditions, you have data which is imbalanced. That is, one class has large number of samples and another class has very less number of samples. How do we learn? And the second aspect is, invariably in real condition, the data that is useful for learning is very, very less. So for machine learning, you need a lot of data. So how do you do data augmentation or things like that? So from our own experiences, we have found that, okay, we have been using neural networks as algorithms for discrimination, but it requires substantial amount of training data. So the question that we asked ourselves is, what do we do when we have limited data? Can we generate sufficient amount of data from the available limited data? So one such approach, we're not saying this is the only approach, but one such approach is what we call it as the S2S learning, simultaneous 2-class learning. So the whole idea is to be able to learn system parameters even from limited data set. So what we are saying is representation of the data for learning effectively from a limited number of trends. So what we did was to modify the neural network so that it can handle more input data. And the motivation for this comes from the way we learn, let us say, the English alphabets. So most of us, when we learn, as kids learn alphabets, we invariably get confused between B, D, P, Q, because they look fairly similar at your learning stage. So one of the ways of learning English small alphabet is, if you show the kid, let us say, B and D together and say that this is B and this is D, probably in addition to seeing the commonality between this B and D, the child would also see the differences in B and D. The fact that B is a 1 followed by a 0 in some sense attached, and D is a 0 followed by 1 in some sense attached, is something that would get into the memory. So it has been shown in literature that such learning often helps the kid learn faster. So this is something that we took into our simultaneous 2-class learning. So conventional learning for a 2-class problem is you take the data, that is X vector ij, and the class C1. So you have a first class and second class, so binary classes. And the Xij could be looked upon as any feature vector. So this is the learning data that you have. And if the number of samples are Ni, for the first class, it is N1, and for the second class, N2. And if they are very imbalanced, then N1 would be very, very small compared to the N2. In the proposed kind of a data sample, what we are saying is don't use just the feature vector in the class, but construct a feature vector of length double the size and give both the classes so that it can learn two classes at the same time. So the whole idea is you are while the feature vector, let us say, is of length d, then the proposed representation is 2D. That is, you put two features together and learn the two features together. So you would not only give the two feature vectors, but you will also give the two classes together, and then you start learning the. So the advantage of this kind of a thing is that from the N1 plus N2 samples that you would have for a ordinary ANN, artificial neural network, now you have N1 plus N2 whole squared number of samples. So look at the amount of training data that has got increased by just looking at the fact that you could learn two samples at a time. So this is a more a figurative way of showing what is this simultaneous two samples neural network. So the top, these two blocks belong to the two feature vectors. You have a huge hidden layer, and the output again has two classes. These the yi corresponding to xi and yk corresponding to xk. Now, once this is learned, let us say, and we have shown in the paper that it doesn't take more time than ordinary feed-forward neural network, the aspect of how do you use it in the test comes into play. So in this case, we need to have a different kind of testing mechanism. So what you do is you take the same test where we have marked as TI, and you select R1 to R capital R some reference samples whose labels are known. So you pass it through the multi-layer perceptron here, but it is in the simultaneous two sample mode. So what you get is outputs YTI, YT, things like that, and you would get your reference outputs as well. The advantage of this aspect of this kind of a network is, since the references are known to us prior, you know which of these are correct. So let us say if the first one was right, then you would select the label corresponding to the test sample. Then you would do a voting based decision to say what is it that the test vector is about. So to just give you a summary of what I just mentioned, so you look at Xij and Xkl simultaneously, and you learn the labels Yi and Yk also simultaneously. In the example that we have shown in the paper, we use the sigmoid and call it the simultaneous two sample learning. And we have been able to show that this kind of learning, when you have limited amount of data, can enable you to learn things much, much better than a conventional thing, because you have more data to train, etc. So one of the things that we tested is for music and speech classification, if you used an ordinary multi-layer perceptron or artificial neural network versus the S2S kind of a scenario that I just described, there is an enhancement of about 4% in terms of the accuracy. So let me cross check. We have about 15 minutes or less. Let us look at what are the practical considerations in machine learning. So let us say we know where all we can use machine learning, and we will not worry about what are the actual machine learning, deep learning kind of a thing that we want to use. But the thing that you would have noticed in the previous lectures is that you use machine learning when you have access to lots of annotated data. You also assume that data is noise free, and you also assume that train and test match. There is a match condition between the test time and the train time. And you never ever exploit any data specific information, and it is a black box learning. And noise-free annotation is something we assume without questioning. But what if you turn it around? What if you said that there's not enough data? What if you said that the data is noisy? What if you say that the annotation may be noisy, or it may be wrongly annotated? And what if you had some information about the data thing? So the deep learning or the machine learning sorts of becomes turned on its head. So if you look at most real world problems, they are in the what if scenario. They are never ever convenient the way the machine learning in theory, or what we learn in theory, can be used. So the data is always noisy, the data is not annotated correctly, and there is no, you have a lot of information about the data, but you don't have any facility to use. So let us look at some of the machine learning aspects in the what if condition. So what should we do when the conditions that machine learning algorithms work best for are turned on its head? So these are some of the examples that I have. Since there is not much time, what I will do is maybe I will take you through maybe one example and then quickly conclude. But before going to that, let me sort of just say that a few of these things are something that we have published and they must be available. Those of you who are interested, if you can kindly get in touch with me, I should be able to provide you references which will allow you to look at this. So the crux of the thing is that you need to be in, from the practitioner perspective, you need to sort of be aware that you will be working on data which is not amenable for what I would call machine learning theoretical application. For those of you who have used the data sets that have been sort of manufactured for testing algorithms, you may not run into these trouble. But once you get into real kind of scenario, the realistic scenarios, you would run into this kind of trouble. So let me take you through one example where I would say, what is it that we did for emotion analysis, where we had knowledge driven into feed-forward neural network. So this is the scenario where there's not enough data, A, and E, which is you have some prior knowledge about the data, and how do you exploit it in a machine learning perspective. So this is the work, this is dated, not very dated, but in 2018, a work which talks about how feed-forward neural networks can use what we call it as driven by knowledge. So some background, since I've picked this up from my earlier slides, it may sound little out of place, but I think it should give you a fair idea of why we are doing what we are doing. What do you mean by knowledge driven? So if you were to look at a feed-forward neural network, what you have is an input I and output O, which are known pair from which you learn. So you update the weights or fine-tune the neural network so that you minimize the predicted output and the actual output O to make sure that and what helps in this is the backpropagation algorithm, which is nothing but the gradient descent in most networks, which allows you to sort of make sure that the O cap, the estimate of the output, and the reference output O are as close as possible to each other. So basically, if you look at it, it could work for any input-output pairs, and there is no need for the network specifically to know anything about the data that is used. Now, if those of you who have worked in this area would know that recurrent neural network, while they need more amount of data, can also exploit, in addition to what the feed-forward neural networks do, is some kind of a temporal, what I would say, information that exists in the same signal. But the feed-forward neural networks never ever have assume any temporal relationship. So even if the data did not have any relationship, that is, the sample that was observed at time t plus 1 might be related to what was set at time t minus 1. But it is also possible that these are random process. But if you were to use RNN, it would try and build some kind of a relationship between the temporal and the sequential data. But for the RNNs to work well, you need substantially more amount of data. You cannot have the same amount of data that you use for feed-forward neural networks and assume that the RNNs will work. And also, it requires some changes in the representation of the input-output pair. Now, the question that one can ask is, what if you had some prior information about the data? Would you still go ahead and use feed-forward neural network, or would you sort of try and fine-tune it so that it becomes this information that you have about the data can be exploited? So the knowledge-driven feed-forward neural network is one such instance where you exploit the information that you have about the feed-forward, about the data. So traditionally, feed-forward neural networks don't incorporate any prior knowledge about the data. As I said earlier, they just treat it as some data points and start learning based on the back propagation algorithm. So the thing that we proposed is feed-forward knowledge-based KFFN, and that's what we call it, knowledge-driven feed-forward neural network, where we say that we have a mechanism wherein we incorporate a priori knowledge into the temporal correlations in the training data. So no change in the architecture, no change in the representation of the input-output pair. Now the question is, why did we do this? Because we were participating in one media eval challenge in 2016. The task there was, given a short video clip, about 10 seconds predict what is the emotion of the person who has seen that video. So you need to be able to do a global prediction for a short video, scene. So 10 seconds of data, build a system to predict the score of the emotion of the person who is seeing the clip. Now, if you look at the whole problem, it is like you have a certain emotional state, V naught, A naught, and you watch the video, and then we go to a final state, VT, AT. So the viewer was at some emotional state, and after which, watching this 10-second video, he went to another state. So what is given is a sequence of videos and the corresponding emotion. So a sequence of 10-second videos, and then annotation which says that this is the valence or this is the arousal. So what are the possibilities is, one of the possibilities is to break this 10-second video into 1-second frames, and so have 10 frames of information, CK0 to CK9 here, and each of them saying that it is some valence VK. So if you were to use a feed-forward neural network, what you would do is you would extract from the n frames all the features that you want, and each of that you would say is valence 1, valence 2. This is the label. But if you were to exploit or want to use RNN, what you would do is you would pass all of them, and only at the last instance you would say that this is the valence V1. So here, if you look at it, every row in the feed-forward neural network is a training sample. In case of RNN, the whole of the top block here is a training sample for the label V1. However, if you observe the kind of data that you have, on the x-axis you have the number of frames, and if you look at the kind of arousal or the valence or the emotional state, when you look at the video, your emotional state is still neutral when you're looking at the first frame. But as you look at the second, third, fourth, fifth frame, your emotional state goes to a value of VK, which is what has been labeled. And after seeing the video, towards the end of the frames, it will go down. So this is the kind of information about the data that was exploited. So what is it that you do? Instead of training a feed-forward neural network with V1, V1, V1 for the first block, you sort of multiply V1 by F1, F2, and Fn, where F1, F2, Fn is nothing but this kind of a trapezoid kind of a function. So F1 may be 0, F1 maybe F3 to F6 may be 1, and again you may be less. So basically what you have done is you have induced in the output labels the information that you had about the data, basically. So if you take this kind of a data and start learning, you could use a feed-forward neural network in the simple architecture that is shown here. So if you have access to this paper, you would find that This kind of a knowledge-driven feed-forward neural network actually enhances your ability to learn the sequential kind of an information that is embedded in the data. The other thing that I wanted to speak was about automatic speech recognition for dysarthric speech. But for lack of time, I'll just skip that and maybe go back to this and conclude this. So if you look at what I've been speaking, machine learning is getting very popular. I had a tongue-in-cheek suggestion saying that every conference seems to have a machine learning section. The reason for this is anybody's guess. There is a lot of data, and the fact that every day we are generating data, there is speech, it means that there is more and more learning data to learn. So every time you use Google, every time you use your mobile phone, you're giving away a lot of data to the outside world. And there are very quick ways of annotation when they ask you for details about your language preferences, from which geography or etc. You are giving away lots of annotation about the data. And all this, remember, is for free. And the second reason why it is getting popular is because of the presence of GPUs, means you can have quicker experimentation, analysis, and more experiments. But the challenges that I described till now remain. From this audio perspective, what are the features? Even from the text perspective, what are the features that we have to use becomes a challenge. There are challenges about annotation, whether it is something that is noise-free or noise-free. Then there are imbalances issue, especially when you're looking at very, very important aspects in terms of medical aspects, where you want to determine whether a particular X-ray belongs to a COVID positive or COVID negative. We have lots of data corresponding to non-COVID patients and very less. And then there are lots of this black box learning issues, the explainability. But in spite of all this, as we can see all around us, use of DNN and machine learning has become very, very popular. However, I would like to caution the following things. What we should be doing as researchers and as practitioners is that try and build explainable AI, especially exploiting the fact that machines are good at certain things and humans are good at certain other things. So we should be able to do this. This explainable AI becomes very important, of course, as we have seen in medical diagnostics, but even more important in the autonomous vehicles. Unless you're able to explain what caused a vehicle to behave in a certain way, you will not be able to sort of tweak or redo the machine learning so that the vehicle behaves in a better way in next time. And the data sense is something that I explained earlier. You need to be able to sort of tell the machine learning, make sure that the data that you provide to your machine learning algorithms are always not missing the things that the information is actually hidden. The classical example is about the warplanes that never returned, which got shot down, which had all the data that was required, which was not part of the learning data. Now, you need to be able to question the data. I've sort of emphasized the fact that you need to be aware how the data was collected. A quick example is one of my colleagues, junior colleagues, attended a machine learning course and came back and said that, oh, I implemented a face recognition using CNN. So we said, we looked through his presentation, and at the end, he had a working system. So we said, why don't you pass an image of a flower, and let's see what your machine learning does. And as you would have guessed, it did put 2 eyes and 1 mouth. Now, the fact is that while we can laugh at this particular instance, it is clear that the machine has not learned the actual eyes and the mouth, but what it has learned is the spatial position between 2 eyes and the spatial position between the eyes and the mouth. So irrespective of the kind of images that you give, it would always put 3 blocks saying that these are eyes and these are. Now, the problem here is not so much the machine learning algorithm, but the fact that you have is kind of input data which had 2 eyes approximately at the same position and mouth approximately at the same position. And truthfully, the machine learning learned the spatial position and not actually the characteristics of the eyes and the mouth. So the important thing is to be able to be aware of what is the kind of data. So you need to be very much aware of the data that you are going to use. For example, I've seen many people use machine learning on news data. So the news data is a different animal altogether, and you cannot use the models built on newspaper data or the news data to do things for other kind of text data. For example, if you want to do some analysis of a journal paper, you cannot use the kind of machine learning that you did for news data. So in some sense, while machine learning is there all over the place, I think there is a lot of things to do and a lot of things to achieve before we can say that we have done something. So thank you very much. And if you have any queries, comments, suggestions based on the time, Professor Patnaik, I'll take.
Yeah. Any queries from the participant side? Anybody?
Yes. So am I audible?
Yes, I can hear you.
Yeah, sir. So since you are the practitioner, I'd like to ask the questions related to challenges while deploying the trained model on the production environment for its use in real life. So suppose that before training the model, I'm doing some pre-processing on the data itself. So in an ideal way, our test image should also be pre-processed before giving it to the model for predicting it. So how do we handle all these things on the production environment? I mean, for testing, because it will give the normal image, it won't predict in a way, it will predict the pre-processed image.
Yeah. See, what I hinted at is the fact that you need to be conscious about the fact that the images that or the data that you get for testing is going to be different. So the way to conquer this is to make sure your learning mechanism or the learning data has ways of conquering these kinds of things. So just to give you an example, if you had noise-free data while you're training, but once you get into the actual production environment, you get noise as part of the data. There's no way your machine learning is going to work on that kind of data. But the fact that if you as a practitioner ask, where is this going to be implemented? What is the data that I have? So maybe you can get a small amount of data and tune your system to capture that kind of a data. So what I want to emphasize here is curated data sets are a different ballgame. The data that you see in the real world are different. You need to be aware of that and exploit appropriate, I would say, common sense aspects to be able to address that.
Right, sir. So another question. The thing is, like, suppose we have deployed our model and it is doing its job, and at the time of like after deployment, we are getting new images from the users or new set of data from the users. So do we keep continuing our model training on production also, or we separately train our model and again put on the production?
Yeah, it is a choice. If you are a Facebook, probably you could do it continuously because your services are free. Nobody would really blame you. For instance, lots of us would have seen, there's a lot of machine learning algorithms running behind what you see on your Facebook page, right? At some point of time, I was
Right,
seeing
right.
all irrelevant messages. Now, the thing is, they have the scenario where they can push such a thing and there is nothing that you can do about it. You'll have to look at it in two ways. Suppose you are an enterprise which is building a machine learning system for a fee, then the customer needs to be aware as to what it is doing. So my own experience is to do anything on the fly is not a very wise thing. You may want to do it at some intermittent points of time when you have analyzed that your machine learning is not doing the kind of thing that it should be doing or something like that, but not dynamically.
Okay, sir.
Right, sir. Right. Got the answer. Thank you so much, sir.
Yeah,
Yeah, you're
I
welcome.
have next question. So in the area of voice
Sure.
disorder detection and classification, there are vocal tract and glottal parameters. These voice disorders, most of the voice disorders are due to the problem of glottal. And if you extract the glottal parameter and if you analyze, so that, it has been observed that there are many disorders, type of disorders that are overlap with each other. The picture vector are overlap with each other.
Sure. Yeah. See, I think Nirmal, I see what you're saying. It all depends on. See, if you look at one of the things that I said, do you want to build a single system which can do everything, or do you want to build multiple systems? Okay, you will have to take a call based on the observations that you have about the data. One of the examples that I gave was, if you see that there is a lot of overlap in the data, probably there is no way you're going to sort of be able to cluster them out, right? So you need to find newer mechanism. My whole idea is that you need to be aware that these are some of the possibilities, these are the challenges, and this is something that you should be able to keep in mind while building. I don't know whether that answers, Nirmal, but yeah.
Yeah, at the same time, we also talk about the voice vocal emotion recognition and classification. So, sir, can you highlight actually what are the current issues and challenges in this particular area? And there are so many databases which are available specifically for primary emotion, but I did not get as such database for secondary emotion.
See, the problem with emotion is the annotation. For example, if I were to be speaking now, and if I were to ask all the 80 people who are there on this call as to how do I sound, I think most of them would either say he sounds neutral, or very few would say he sounds. But there is going to be a lot of disagreement,
Yeah, yes,
because
sir.
the perception of my interpreting somebody else's mood depends on my mood as well. So there's a lot of these kinds of aspects that make the problem difficult. So that's why if you look at the emotion literature, the kind of accuracies that you achieve are very less. But there is no way you can get over that. You'll have to think of newer ways of doing it. You'll have to look at probably building some kind of trying to get some kind of a consistency in the annotation that you get. So there are a lot of things that you'll have.
Sir,
That's what makes this.
Sir, without annotation, suppose if he directly prepare the model as per the characteristic of the data, it means instead of labelizing it, if he prepare the model by means of Gaussian mixture model, okay, model with respect to the emotions, and afterward actually we test it. So, what is your opinion about it instead of annotation if you directly model it?
Yeah, see, the modeling requires you to extract features, right? You'll have to extract some features. So there you have made a decision. See, the whole point of machine learning is that it should sort of stop you from making a choice of the features. And why this is an important aspect? Once you say that I'll use a certain kind of feature, either it is because it is famous in literature and it has worked very well, or maybe from your own experience you have used it, or maybe it is easier to extract. But that is not the complete thing. The machine learning aspect is to be able to give it data in its complete sense. Maybe there is something else which we as human have not seen. If we have not seen it, if we are avoiding, or we are not enabling the machine learning to exploit that kind of an information. So I think once you talk about machine learning, I think what you should start doing is looking at raw data. Okay, from the speech angle, the raw data invariably is as the spectrogram. Okay, so we'll have to make that kind of a move. Otherwise, what will happen is you will be restricting your thing to just the kind of features that we know. At one point of time, I was looking at what are called no sense labels. So we are limited by what we know. For example, when you look at a emotions, we say that, okay, what is easy, angry, neutral, whatever, 4 or 5 emotions. But there may be something which is neither angry nor neutral, but in between.
Yeah, correct.
So there is no strict degree, 0, 1 kind of a thing.
Yeah.
And if you ask for annotation of that kind, it's just impossible.
It's quite difficult, yeah, I know. But at the same time, what is your opinion about the secondary data, secondary emotion? It is again difficult.
To me, it is from the practical perspective, it is the following. If I, as a human being, cannot judge it correctly, then I will not be able to evaluate the performance of a machine. Okay. So I think we'll have to sort of circle around that and see what is the best we can do. See, the example that I said, if a machine learning learned something and said something, but my own limitation doesn't allow me to gauge whether it's right or wrong. So I cannot really use that information.
Yes, sir.
The machine must have learned something, but I don't know what it is. So the explainability becomes an important aspect.
Yes, sir. Thank you, sir.
Thank you.
Sir, am I audible?
Yes, yes.
Sir, actually, your session was very informative, actually. Only a small thing I wanted to ask you. Sir, generally, machine learning models are used for classification. But if we want to use this for estimation type of problem, like let us say any wireless channel parameter estimation, like all these JAX model or IEEE 802.11 channel models, or any estimation, maybe in smart grid environment. So what type of model can we use in those applications?
Okay. So probably this is little different, but I'll try and answer it in the following way.
Okay.
If you look at from the machine learning perspective, you need data, right? Whether you understand the data or not. So when you want to do such a modeling, that the kind of thing that you are asking, first thing to ask is, what is the data that I have that I can use for learning? So even without my knowing anything about the problem that you're saying, if I have that kind of a data, then probably I can machine learn that in the blind way. Okay, may not be the best way. I don't say you should do that, but at least you'll have to ask yourself, what is the information that I have? Okay. The second thing that one has to keep in mind is that why do you want to model it? Is it that it's not something that is already theoretically modeled? What I mean by that is, suppose you know that these are the components of these and these are the uncertainties, and hence if I can model it in this way, it characterizes that. If it does that, then there's no point in trying to model it. So the thing is, while this may not be a perfect example, but I can't think of anything else. Suppose you want to add 2 numbers.
Okay.
The question to ask is, do I want a machine learning to do that?
Okay.
Because look at it from the data perspective. If machine learning, if you believe that it has to have seen the data, the kind of data to expect to learn what is called an addition, you cannot give it all the data that you have, because your test data could be coming from a set which is different from the set that you have.
Okay.
So, yeah, I know I didn't answer your question.
No, it's okay. It's okay, sir. But actually, what we have seen in many papers, they are using ELM, extreme learning machines, for all these kind of problems. That ELM model is working well, which is also a category of machine learning. But exactly this LSTM or RNN, these type of applications are very rarely found in this communication field, mainly wireless communication and all. So anyway, sir, thank you very much for your answer.
Yeah,
it was okay.
So my question is a little bit related to the speech processing. When you do any kind of modeling of the speech data, basically you take the data from the available data sets in the internet or some other place. So we model that one. But when you deploy the same model in a real-time environment, it basically fails. So, I want to know your perspective of approach for this kind of application. Is it better to go for modeling the data in the noisy environment itself, or if I take the noise data, then I go for a speech enhancement kind of task, then go for motive. So what would be the right choice
Yeah.
for the
Yeah. Yeah. Actually, in literature, if you see what people would generally try to do is you would push the kind of expected scenarios into your training data set. So there are mechanisms of adding noise or increasing your data set to increase some kind of a push in noise. So immediately from the literature perspective, you would say that, okay, take noise X92 database, mix it, learn it, and then test it.
Yeah.
What we did is sort of try and generate noise. So we found, this is one of the patents that we recently procured, we found what is called a noise basis. So like the Fourier transform has a basis, we came out with what is called a noise basis. So if you sort of what I would say, weighted some of this noise basis, you could create a noise of certain kind. So in reality, we somehow span the whole space called noise using this basis. So what we are doing currently in the lab is trying to generate noise without actually, what I would say, recording any noise per se. We are simulating noise, and then we are pushing into the data and learning on that data. So this seems to be working very well in the realistic.
You say that it is synthesized noise data?
Yes, yes. See, noise is also a very expensive proposition. You need to go collect noise, realistic noise. You need to be so a lot of time and money is spent on collecting data. So if you can simulate all the data, noise data, without actually collecting, it is quite a useful thing. Okay. So then I want to emphasize one thing, like speech enhancement, unlike image enhancement, is a different ballgame altogether. Our own observation has been that you can do speech enhancement, but your intelligibility doesn't increase. Your speech to text accuracy doesn't increase. Though it may sound very good to your ear, it doesn't translate into ASR because of the mismatch in the training and the test data set. So
how about in the diagnostic area, like the medical aspect, the pathological speech specifically? So we don't need their the intelligibility in a much better way.
Yeah, I couldn't hear you completely, but many things are task dependent. Okay, so you will have to see where you want to do what you want to do. So if you look at my presentation, I had a very specific thing saying that you need to be looking at specific kind of application. Then you have problems or challenges that you will have to address. See, I don't want you all to mistake that I have solved all this thing. My thing was to highlight these are the challenges. You need to be aware of them. You need to be able to tackle them. And my emphasis was that there are ways of doing it, and it just needs you to think about it. So the final one sentence summary that I would like to say is that don't look at data as data, but give it the human intelligence that we all have, right? We are all brainy people. We know what we are dealing with. Never look at it as data the way the computer or the machine would look at. Give it a little more color to the data, and then I think you will be able to solve practical problems. Okay, don't assume that I have solved something. These examples are only in certain areas where we have found successes. So I just want all of us to keep our eyes open and look at data not just as numbers or not just as data, but color it with the knowledge, world knowledge that we have, and that data becomes a little more amenable for machines to learn. Okay.
Thank you, sir. There's another one more question. Like, so you mentioned the listener's perspective and the observer.
Mr. Susantu, I would like to stop you because already we are exceeding the time, and again we have another session. And later on, whatever queries you have, already I have shared his email with you. So you can be in touch with him.
Yeah,
Sorry.
yeah.
Yeah. So anybody having any more queries, I suggest that you be in touch with Dr. Sunil Kumar, and he is very good in responding. Anytime I write to him, immediately I get the response from him.
Yeah, yeah. Okay. What I suggest is just mark in your header that this is the context. Okay. So I might get more emails, but I will if I know the context,
Yeah,
it's easy.
yeah, the subject, yeah.
Yeah.
Subject field you can write that is, yeah. So thank you, Dr. Sunil Kumar. So
Yeah.
though I said that it will end at 1 p.m., now I can see that it is approaching to 1:30. So sorry for making it so late. So it
No.
was really interesting. You highlighted so many challenges, so you can pick up any of these challenges and start working on it. Thank you again. So participants, again, see you at 3:30 p.m.
Okay, ma'am. Thank you so much,
Yeah,
ma'am.
yeah.
Thank you all.